This is Grand Admiral Rosine, following the physics directive to explain conceptual modern physics. In this video, I will be explaining time dilation, Lorentz length contractions, and mass energy equivalence. In the previous video, we discovered the relativity of simultaneity and got our first taste of Einstein's relativity as a whole. We have not yet addressed the first thing people tend to think of when they think of relativity: time dilation. First, we can understand time dilation on a spacetime graph. We will take two events, marking the position of a particle at rest in the blue reference frame at time equals 0 and time equals 1. You will see that, even though its position changes in our rest frame, it stays at 0 in the blue reference frame. This shows that position is relative, which is necessary for motion to be relative. The other thing you may notice is that these events are not 1 unit of time apart in our rest frame. This demonstrates that time is also relative. Because the particle is in motion, 1 unit of time to it takes longer from our perspective. But remember that motion is relative. From the particle's perspective, we are the ones in motion. Since 1 unit of time to the particle takes longer to us, one would immediately assume that 1 unit of time to us takes less time to the particle. But since we are moving from the particle's perspective, what actually happens is that 1 unit of time to us takes longer for the particle. We can confirm this on the spacetime graph by marking our position at time equals 0 and time equals 1. Sure enough, the particle views those spacetime events as more than 1 unit of time apart. Because the differences in time are relative, this is not time travel. However, we will address actual time travel in the next video. Time is not the only thing that is relative. Space is as well. We can prove this by taking two simultaneous points in the blue reference frame. These represent the ends of a spaceship and are 1 unit of space apart. The spaceship is at rest within the blue reference frame, so we can draw the world lines of both ends. From our rest frame, simultaneity changes. When observing the spaceship from our rest frame, we would see its ends at simultaneous events. Because of this, you will notice that the spaceship would actually appear shorter in the direction of its motion from our reference frame. Similarly to time dilation, if we were on a spaceship, the original spaceship would view us as shorter in the direction of our relative motion. Time dilation can be demonstrated using light clocks to provide a more conceptually pleasing explanation for it. Take two spaceships with mirrors that reflect a particle of light back and forth. When these spaceships are at rest, it takes exactly 1 unit of time for the light to reach the other mirror. Now, say one spaceship is moving upwards. Because of the Pythagorean theorem, light would have to travel a longer path to reach the other mirror. But its speed is constant in all reference frames, so to the pilot at rest, it takes longer than 1 unit of time for the light to reach the other side. But to the moving pilot, the pilot we said was at rest was actually the one moving. Therefore, the same exact effect would be observed, preventing time travel. Lastly, with the existence of time dilation and Lorentz contractions, it's easy to wonder, what would happen if someone moved at the speed of light? Well, we can first view this on a spacetime graph. Remember that the world line of a moving object within our rest frame becomes the time axis of that object's rest frame, and then the space axis gets tilted by an equal amount. Also remember that the speed of light is always at a perfect 45-degree angle since we referenced our spacetime graph to it. This means that both the time and space axes would tilt at a 45-degree angle, merging into a single axis. While it seems as though this means spacetime only has one axis to light, the truth is that light simply has no perspective. If it did, then the speed of light couldn't still be c from its own perspective. This seems like a scary possibility, since according to Newton's second law, if we apply a force for a long enough period of time, we should be able to reach the speed of light without any difficulty. But if the speed of light is constant in all reference frames, and a person always views themselves as being at rest, then wouldn't it always be greater than your speed, preventing you from ever reaching it? But if you can never reach that speed in any reference frame, and a constant force was applied to you, The acceleration from that force would have to decrease the faster you went within a different reference frame, making it impossible to reach the speed of light. This is the case, and it is because of mass-energy equivalence. A common misconception is that E equals mc squared means mass can be converted into energy. This is not true. You see, mass is a form of energy itself. Therefore, as your relative speed increases, your relative kinetic energy increases, so your relative mass increases. This makes your resistance to acceleration increase, preventing you from reaching the speed of light in any reference frame. In the next video, we will discover actual time travel, not just time dilation, and also will explore why causality is preserved despite the relativity of simultaneity. By the end of the next video, you will understand the special case of Einstein's theory of relativity. If you enjoyed this video, please give it a like. If you wish to further explore conceptual modern physics, subscribe to my channel and join me in the Physics Directive. Long live the Empire.